Imagine two metallic spheres floating isolated in a perfect vacuum. They have no physical connection to each other or to anything else in the universe. This first sphere has two distinct properties: a specific size, its radius r1, and a certain amount of charge, labeled q1. The second nearby sphere has its own rules: a different radius, r2, and a different initial charge, q2. Right now, they are entirely separate ecosystems, but what happens if we force them to interact? Once we connect these two systems, the rules of physics have to decide exactly how they'll share their resources. The intuitive guess is that they would simply pool everything together and split it right down the middle, a neat 50-50 split of the total charge. But physics rarely works like a polite compromise. To find out exactly how they rebalance, we have to map this out mathematically. Looking at these technical notes, we can build a predictive model based entirely on their physical geometry. The moment we connect these two spheres with a conductive metallic wire, that isolation ends. The connection instantly sparks a chaotic, high-energy flow of charge rushing violently from one surface to the other. This violent transfer is temporary. The note explicitly states, after connecting them with a metallic wire, flow of charge stops. This flow is driven by electrical potential, or V. In the first column, V1' equals V2'. That equation is the condition for equilibrium. The charge stops moving the exact second the electrical pressure, the potential, equalizes across both spheres. Expanding that out, we see how potential is calculated. The equation shows pressure is determined by the ratio of new charge divided by physical radius, multiplied by standard emitfical constants. Because those universal constants appear on both sides, we completely cancel them out of the math. That simplification leaves us with the final equation here at the bottom of the column. It tells us the second sphere's new charge equals its radius divided by the first radius, multiplied by the first's new charge. This ratio proves something fascinating. It is physical geometry, not just the initial charges, that dictates the final energy. But to solve for the exact final numbers, we need a second fundamental rule to anchor the math: the law of conservation of charge. Moving to the middle column, this equation states a simple truth. The total combined charge after the connection must mathematically equal the total combined charge we started with. No energy is lost. Now we combine all of our mathematical findings. We drop that geometric ratio directly into this conservation equation, substituting q2'. In the third line, we algebraically factor out the first sphere's new charge, setting it equal to the initial charge. By combining equal pressure with the unbreakable rule of total conservation, the math isolates our variables. The system is now locked into a single, highly predictable physical outcome. That brings us to these final synthesized formulas boxed on the far right. They give us the exact calculation for the new charges on both spheres. In plain language, a sphere's final share of total charge is simply its physical size divided by the system's total size. For example, if one sphere is exactly twice as large as its partner, to reach equilibrium, it will hoard exactly twice as much charge. This exact geometric sorting happens all around us. Engineers rely on these precise proportional rules when designing microscopic capacitors for electronics, and it's the exact same mathematics governing how massive storm clouds distribute electrical charge right before a lightning strike. Nature will always relentlessly seek a state of balance, but the final distribution of resources in that balanced state is permanently dictated by physical geometry.